Thank you for joining me for today's video. This is Mr. Ish. I hope everyone's having a nice day. I want to start today with binomial theorem. It can be a rather messy and difficult topic. Maybe I might decide to split the video or this whole subject matter into two videos rather than one. But let's see how it goes with this video. Binomial. This right here is an example of a binomial. To understand the binomial theorem, you have to understand and know several other skills and trends before we can tackle this topic. We've seen binomials, and this right here is a letter n, which represents an exponent. This right here is an example of a binomial. We know this because we've seen it and we've used it, a plus b whole square. The whole concept of binomial theorem is to be able to open and expand. And this can be a minus in here, it doesn't have to be a plus. So think of it as a plus minus b to the power of n. We know we've seen this because in factoring we've done it. Plus 2ab plus b squared. So what's the whole concept behind binomial theorem? You're given a binomial meaning two terms to a whatever exponent, and you have to learn how to expand that. And you have to notice a couple of trends before we can start expanding. And let's look at some trends first. Then we look at some of the basic techniques we have to know for the binomial theorem. I'm going to erase this line over here and show you some trends that arise. Let's look at these examples for the trends. A plus b whole square to the power of 0. I'll open it up momentarily. A plus b to the power of 1. A plus b to the power of 2. Remember the signs in here could have been minuses. I'm just using pluses out of convenience. And using pluses is always easier than using a minus. A plus b whole cube. Let's open this up. A plus b all to the power of 0. What do we get? We'll get 1. Remember I said in another video, anything to the power of 0 is equal to 1. Let's look at a plus b to the power of 1. What do we get? A plus b. Anything to the power of 1 is exactly the same thing. Just remove the parentheses and you end up with the same thing. And I just showed you this momentarily. 2ab plus b square, a plus b whole cube. These are all things we've naturally gone up to cubes in basic algebra. A cube plus 3a square b. This is one of those formulas where we have memorized in the past, plus b cube. Let's look at this. What are we? I'm seeing a clear trend over here. Anything to the power, well, let me restate that. Anytime we have whatever exponent, the number of terms we get when we open this binomial is always one more. We have an exponent here of 0, we get one item out of that because 1 is one more than 0. We have an exponent here of 1, but we get two terms. See, we have two terms, 1, 2. The number of terms you get from expanding a binomial is always one more than your number of exponent. Look down here at 3. We have an exponent 3, but when we opened it, we ended up with 4 terms. 1, 2, 3, 4. So the first trend we have to know is whatever this n is over here, when we'll open it up, right, we'll have n plus 1 terms. By expanding it, if we had a 7 over here, we should end up with 7 plus 1 or 8 terms. So that's the first trend you have to know about binomial theorem. The number of exponent increased by 1 is the total number of terms you'll get, whether it's a plus or minus. That's the most important trend of binomial theorem. And keep that in mind. That n plus 1 rule. Let's look at another thing we need to know about binomial theorems. We need to know, and this will play into a trend that I'll show you later on, what this right here is. N capital C R. N capital C R has to do with factorials and combinations. This is what is called a combinatorial, I'll call it a combinatorial product or a combinatorial format of showing something, and it is equal to n or in parentheses. But what does this actually mean? N or. Anytime you're using doing binomial theorems, you're gonna be thinking about this, and you may have seen this in terms of combinations and permutations when you've done probability and statistics. But with regards to binomial theorem, this implies this, which implies this right here. N factorial, and I'll show you this momentarily, r factorial n minus r factorial. Why do we have to know this specifically? Because of this reason alone. If I showed you this as an example, and I did momentarily, you know we had this as our answer, 3a squared b plus 3ab cubed, 3ab squared plus b cubed. The only reason why we have to know this is because you're seeing their coefficients here. Here's a 1, here's a 3, here's a 3, and a 1. You have to know this rule over here to know what these exponents will be when you open up any binomial. Look at this. These are symmetrical binomials. A and B have coefficients of 1, so you end up having symmetrical answers, but not always. You could have had a 2a and you could have had a 5b. They're no longer symmetrical, having the same coefficients. They could have had different coefficients. But no matter what these coefficients are of a and b and what the coefficients will be in the final answer, you have to know this rule to determine what these coefficients are. And remember, coefficients are the numerical values of these variables. These numerical numbers, that's a coefficient. You need to know this rule to determine these coefficients. So let me show you another trend you'll see for binomial theorem. Whenever you expand a binomial theorem, you can see you're always working from one letter and ending up to the other letter. See, here's one letter, here's another letter, a and a b. As the exponent increases from positive to a 0, the other letter's exponent, as one exponent decreases from 3 to a 0, the other letter's exponent increases from 0 to a 3, or whatever that number could have been. Look over here, a started with a 3, then it went down to a 2 exponent, then it went down to a 1, then it went down to a 0. There is an a here, except it's a to the power of 0, which is 1, and we neglected to show that. And look at b. b is present here, but it's present as a b to the power of 0. Then b is present here to the power of 1, then to the power of 2, and then 3. So that's another trend you need to be aware of. 4 terms, because there's 3 over here, n plus 1 terms. So whatever the number here is, you add 1 to it, that's the number of terms you'll get. And the variables will go sequentially. As one sequentially goes down from the highest number to 0, the other one will sequentially increase from 0 to the highest number, the exponent. Alright, from 0 to 3 and then 3 to 0. That's the trend you need to be aware of. Let me show you how this combinatorial product plays actually in terms of solving. For that, you have to know what a factorial is. These exclamation marks are called factorials. Here's a quick example of a factorial. Anything to this factorial is always equal to that same number multiplied by all the consecutive numbers which come after it, but downwards towards 1. Never up to 0, but always up to 1. 5 factorial is the sequence of the products of all the numbers, including 5 all the way up to 1. You can calculate that and you know that'll be 120. 7 factorial will be the sequential product of all the numbers from 7 all the way up to 2 and 1. Sorry, all the way up to 1. Not 0, because if you put a 0 here, you'll zero everything out. And you can imagine what 11 factorial could be. It would be 11 times all the numbers all the way up to 1. And that product is what this factorial equals. So let me show you an example of how you calculate the combinatorial product, which represents the coefficient of a binomial element. If supposedly you have something which looks like this, 6, 3, the first number n always represents what your exponent is for that binomial. Look at here, this here is my n, this here is my r, and this represents something which may have looked like this, a plus minus b to the power of 6. This n over here, which is the value, which is the number 6, always is representative of this exponent of that binomial. So how do you actually solve this? You solve it by plugging into this equation. You know 6 here represents my n, r represents 3, so you do 6 factorial divided by 3 factorial multiplied by 6 minus 3 factorial. You can calculate this. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is a 720, divided by 3 factorial, which is 3 times 2 times 1, which is a 6, multiplied here in the denominator by another 3 factorial. So you're essentially having 6 factorial divided by 3 factorial and 3 factorial. And you can calculate this out and you can obtain a number. And sometimes if you don't have a calculator, you can actually cancel things out. Like 6 factorial, you know, is a 6 times 5 times 4 times 3 factorial, because 3 is still 3 times 2 times 1. And here you had a 3 factorial times a 3 factorial. Well, these 3 factorials here can cancel out. Then you can cancel this out with this 6, because you know 3 factorial is a 3 times 2 times 1. So this cancels this out. So all you're left with is a 5 times 4. And you know this now is a 20. Let's look at another example of this combinatorial calculation. Imagine if you had this as an item 4, 1. Here's my n value, here's my r value. So you'll write as this. This is my n, this is my r, which is the same thing as 4 factorial over 1 factorial and 4 minus 1 factorial. And you'll have 4 factorial over 1 factorial is meaningless because it's just a 1. Essentially divided by 3 factorial. And you know if you calculate this, it's equal to a 4. Because the 3 factorial will cancel everything after this 4. 4 times 3 times 2 times 1. All of that will cancel out with this 3, leaving you with just a 4 on the top. Let's look at one more example before we get a little deeper. Let's look at this. A 5 and a 0. Write it out as you see it. 5 on the top because you have n on the top. Here's my n value, here's my r. And you put a 0 down over here. And you expand this out in this format. 5 factorial divided by 0 factorial, meaningless. 0 factorial is not 0 in that sense. You're not going to be thinking you're dividing something by 0. It isn't. You just remove it. Over 5, multiply by 5 minus 0 factorial. Remember this n minus r? That's my n minus r. So what do you get? You get 5 factorial divided by 5 factorial. It all cancels out and you get a 1. So don't confuse a 0 factorial as being a 0 and that you'll get an undefined because you end up with a divide by 0. In this case, 0 factorial, meaningless, remove it out and just keep working. So that's the combinatorial product that you have to be aware of. Remember, these represent the coefficients of the expanded binomial. I want to show you an example in terms of the theory. Then we can look at practical applications. Let's look at this example, a plus b to the power of 4. And you know I've mentioned few trends already. The exponent being one of the trends. If you have a 4 over here, you increase it by 1, that's a 5. We know if you were to expand this binomial, we'll have 5 terms. So this should equal into 5 separate terms. Another trend we've seen is as the exponent of 1, as you're going along this expansion, as it decreases from the highest exponent, which is what you see here from 4 to 0, the other variables, exponents across that series will increase from 0 all the way up to 4. The procedure for expanding this, as I've shown you, requires the combinatorial product because that's going to represent your coefficient. So let's see all of that. And we know this is an nr, which represents an n factorial or r factorial n minus r factorial. I want to show you this example specifically in terms of the theory behind it. How will you expand this out? You'll expand this out by using this following formula. You'll start with your n and r. N is always what you're starting with here. This is your n value, right here, n. R, you're starting always with a 0 because you're going to work up this r value up to your n. 0 will work up to 4. You're going to write your first term. Here's my first term. And that exponent for the first term will always be n minus r. See, here's my n term, here's my r term, n minus r. But look at this, what's my n over here? It's a 4. What's my r? Is a 0. Right, so 4 minus 0, this will actually be a 4. See, the exponent will turn out to be a 4. Let's look at the b term. See the b. And right now we're only on the first element of this 5 series expansion. The exponent of b over here will be r. Whatever you see here as your r, that's the exponent. But what's r over here? It happens to be a 0. This is my first element. Let's show you the second element. This element right here, 0, is going to increase by 1 unit, which will correspondingly affect these exponents. What will happen to a? It'll become n minus r, as you know. But here, n and r is a 4 and 1, which will be a 4 minus 1. See, a 4 minus 1, which will become an exponent of 3. What will happen to b? b is always having the exponent of r, whatever that might be. Here r equals 1. See, r is equal to 1. Let's look at the third term of this series. Remember, we should have 5 terms. Here a will have again n minus r, which will be a 2, and b will have an exponent of r, which here is a 2. Alright, always stay in this way. Let's look at our next term. These are all pluses, everything will be pluses. See, we're correspondingly increasing the value of r, 0, 1, 2, and we're going to stop when this 2 becomes a 3, and when it becomes a 4, then we have stopped. This is my fourth term. You see how we got a 4, 3 over here? Now a is again always n minus r. See, n minus r, which will be a 4 minus 3. See, 4 minus 3. These are your exponent values. What happens to b? b is always r. Here r happened to be a 3. I'm going to write this out all cleanly right after this. And last term, the fifth term. n, r, 4 and 4, when these even out, the same numbers, you know you're going to stop. Here again exponent n minus r, which will be 4 minus 4, which will turn out to be a 0. You see how we started with a to the power of 4 and now a is going to become a power of 0. b started with the power of 0 and sequentially it's increased to a value of b to the r, which happens to be here a 4. You see how b has become a 4? Now let's write this in a clean manner just by erasing the exponents. n minus r here was a 4 minus 0. So that became to the power of 4. See? 4. b here was a 0. So it started out with a power of 0. n minus r here for the second term was a 4 minus 1, which is a 3. So the exponent for a became a 3. b here had the exponent of this r value, which is 1. Let's just write that 1. And you'll see this trend coming across. Here exponent of a is a 4 minus 2 n minus r, which is a 2. Let's put this 2 over here. The exponent of b is always the r value. Here it's a 2. Let's eliminate this r over here so it's clean, nice and clean. b to the power of 2. Let's come down over here. Exponent of a here is a 4 and a 3 minus a 4 and a 3, which is n minus r, which is that 1. Let's put that 1 over here. And b here is exponent r. Let's eliminate that r and just keep the 3, so it's b to the power of 3. Lastly, a here is n minus r, 4 minus 4, which is a 0. Let's put the 0 over here to the power of 0. And b is always a value of r, which is just a 4. Let's bring this 4 over here. Is our answer complete? No, it isn't, because I still have yet to even solve the coefficients. I have done nothing with the coefficients. Remember this rule, nr is equal to n factorial or r factorial n minus r factorial. All I've done is expand the entire binomial to the 5 terms, n plus 1, 4 plus 1, 5 terms. I've managed all the exponents, but I've yet to do something with the coefficients. Let's solve the coefficients. If you put 4 and 0 into this formula, you'll actually end up with a 1 over here. Because you'll have a 4 factorial over a 0 factorial times a 4 minus 0 factorial. 4 factorial or 4 factorial will be 1. You'll have a coefficient of 1. If you solve this 4 and a 1 over here, a 4 factorial and a 1 factorial, you will eventually, running it through that formula, you will get a 4 factorial divided by a 3 factorial, which you can run it with your calculator, will be equal to a 4. Let's do this. A 4 and a 2, run it through this formula. If you run it through it properly, you'll get a 24 divided by 2 divided by 2. You can take my word for it. That'll be a 24 divided by 4, which is a 6. Remember, you can use a calculator for everything over here. Next, 4 and a 3. You run it through there, you'll get a 4. And I'll show you one last trend before we end with this example. It's a trend of symmetry. Lastly, 4 and a 4. You run 4 and 4 here. You'll 4 factorial or 4 factorial and a 0 factorial. Remember, 4 minus 4 will give you a 0. So you'll essentially have a 4 factorial divided by 4 factorial, which is the same thing divided by the same thing no matter how long that sequence might be, and it's still equal to a 1. So what's our final answer? It's a to the 4th. Never write exponents with the zeros because they're always 1. Plus 4a cubed b plus 6a squared b squared plus 4ab cubed finally plus b to the 4. You can see all the trends in here showing up. Trend number 1, 5 items from a 4 exponent binomial. Trend number 2, the exponents of one gradually decrease one by one till it hits 0, where the other exponent increased gradually from 0 until it hit the maximum exponent. Here's your maximum exponent. The last trend is the trend of symmetry. Right here, look at the symmetrical coefficients, 1, 1, 4, 4, and a 6. It's like a pyramid. It's symmetrical pyramid. And the only reason why you'll have these symmetrical coefficients is, if these coefficients are symmetrical right in here, you'll have a symmetrical answer. See, 1a, 1b. If you had a different coefficients here, you'll lose the sum of this coefficient symmetry. You won't lose the symmetry of the exponents, but you lose the symmetry of the coefficients. As a final closure to this video, only in terms of theory, I want to bring up the concept of Pascal's triangle. You've probably heard of this, but here's what it exactly means. Look at it. It looks like a pyramid, symmetrical. In terms of how each row is symmetrical with regards to each other. And we're here talking about symmetrical binomials. See, coefficients of 1 and 1 to whatever power. This first row number is generated from that a plus b to the power of 0. You have, as I shown you before, one term and it has a single term called 1. And you know this comes from a plus b to the power of 1. You open it, you get a plus b, which is 1 and 1. The coefficients are 1 and 1. This comes here from a plus b whole square. A square plus 2ab plus b square. Looking only at the coefficients, again we have symmetrical starting points, symmetrical answers. And look at this, a plus b whole cube will generate a symmetrical another row, a cube plus 3a square b plus 3ab square plus b cube. And the example I just showed you before this was a plus b to the power of 4. A to the 4th plus 4a square 4a cube b plus 6a square b square plus 4ab cube plus b to the 4th. You can imagine if we had a plus b to the power of 5, what we would have. Just by using the Pascal's triangle, it would be this. We'll have 1 at each end. And now look at the last trend I'm going to show you. Each of the middle numbers in each row is the sum of the numbers above it. You look at this. This number 2 is the sum of the two numbers directly above it, 1 plus 1. Look at this 3 is the sum of the two numbers directly above it, 1 plus 2. Same, 3 was the sum of the two numbers directly above it, 2 plus 1. This 4 was the sum of the two numbers directly above it, 1 and 3. This 6 was the sum of the two numbers above it, 3 and 3. This 4 was the sum of the two numbers, 3 and 1. You can imagine what number will fall over here. It'll be the sum of these two numbers. It'll be a 5. These two numbers, 6 plus 5, add up to a 10. 6 plus 4 add up to a 10. 6 plus 4 add up to another 10. 4 plus 1 add up to a 5. So now, using the Pascal's triangle, we can know exactly, without using the binomial theorem, what the answer would be. Remember, for symmetrical binomials, it would have been a to the power of 5 plus 5a fourth to the b plus 10a cube b square plus 10a square b cube plus 5a to the b fourth and b to the 5. You see, as I had to pay a little extra attention over here with the exponents. As I was decreasing one exponent from 5 to 0, I was increasing the other exponent from 0 to a 5. So that's the concept behind the Pascal's triangle. For symmetrical binomials, you can keep expanding this downward and you can keep knowing the number of the terms and the coefficient of those terms as you expand them out. And again, it is in keeping with the number of terms for each exponent. See, 5 exponent but 6 terms. 4 exponents, 5 terms. 3 exponents, 4 terms. 2 exponents, 3 terms, and so forth. I hope you enjoyed this video. In the next video, I'm actually going to show you the types of questions you'll see when it comes to binomial theorem. And we will be using non-symmetrical binomials to make it a little more challenging. You also have to be familiar with learning how to expand a large binomial or find only the specific elements of a binomial. By that I mean, if supposedly there was a question like a plus 3b to the power of 10, find me the 6th term without even expanding this. How would you calculate what the 6th term is of this? You know this would have 11 terms, but what would exactly that 6th term be? So we'll be looking at all of that in the next video. Thank you for watching this video. Please like and subscribe and share. Have a good day. Bye.